Welcome to KCC Diesel Online. My name is Jeff Rush, and this is DST 110H. Today we'll be covering Chapter 6 out of our text, and this is Basic Electronics. I really don't like the term Basic Electronics because there's really nothing basic about electronics. I think it's it's a oversimplification, but it's like saying simple right-angled trig in my opinion. For those of us that are struggling with right-angled trig, then it's not simple. For those of us that excel at it, then it's simple. So most of us in the diesel industry are not going to excel at electronics. We're going to excel at basic wiring. We're going to excel at being able to diagnose basic electronics. But we're not going to excel at electronics itself. So let's go ahead and move to our learning objectives. We're going to list the various types of resistors. We're going to determine whether or not a diode is forward biased or reverse biased, and we'll talk about what that means. We'll test a diode with a digital multimeter. We'll explain the function of a Zener Diode, and we'll describe the operation of a bipolar transistor. Explain the difference between a transistor being used as an amplifier and a transistor being used as a switch, and what that means. Describe the operation of a field effect transistor, or a FET. You're going to hear that term a lot in the diesel side of the house. Maybe not quite as much in the automotive side, but I think that this is becoming a more popular term. Instead of calling things, a fuse inside the module, we're talking about what it actually is, which is a field effect transistor. And we'll discuss the concept of a high side driver and a low side driver. All right, resistors. The whole point of a resistor is to limit the current flow through a circuit. We also divide voltage with it. A resistor uses the voltage and gives off heat. So remember, our voltage has to be used in some way. It has to be light, heat, or used in a solenoid or a motor. Got to use it in one of those three ways. Two main types of resistors are fixed and variable, so we'll talk about some examples of both. So fixed resistors have a color code, and as you look here on the banding, we have our first band, our second band, our third band, then we have a multiplier band, and then a tolerance. So our first band is going to tell us, by the colors, what our number is there, and then our second band and our third band, and then we're obviously going to have our multiplier. So whatever number that we come up with from the first three bands, is that multiplied by 1? So it's a 100 ohm resistor. Is it multiplied by 10? Is it a 1,000 ohm resistor? So as we go through there, that's what you're going to find out. And then the resistance tolerance is how accurate, how good is this resistor? Is it accurate by 1%, 5%, 10%, minus, above or below what we think the value actually is? And you'll find out on some of the resistors there's a bit of a tolerance issue. All right, stepped value variable resistors. So one of the places you're going to see this is in our rheostat. Okay, here we have basically a winding crossing our resistors, and depending on where we're pointing, that's how much resistance we're going to get in our system. All right. Here we have an infinitely variable resistor, meaning it doesn't have a set number of resistors. From point A to point C here, we have infinitely variable resistance, just depending on how our resistor winding needle here is pointing. And one place you would see this is in an old style Ford dimmer switch for the interior lights. Or for the dash panel lights, I should say, for the gauge lights. All right, here we have a potentiometer. Okay, so here's our resistance. So we have a 10K potentiometer. But with our potentiometer, again, we're adjusting that voltage based on where this needle is on our resistance, or on our resistor, I should say. All right, semiconductors. A material that is neither a good nor a poor conductor. Okay, so it's a semiconductor. Silicon is the most commonly used in electronics. Semiconductors usually have a negative temperature coefficient. Pure silicon has 4 valence electrons. Impurities added to silicon is a process called doping. Okay, doping a material that has excessive electrons creates an N-type junction. Doping a material that has an excessive holes creates a P-type junction. Okay, and we'll talk about what that means. So here's an N-type. So N-type semiconductor doped with arsenic. Okay, I think we've all kind of heard that. Arsenic is a popular ingredient in rat poison. So here we have our extra electron in our N-type. Okay, N-type semiconductor doped with arsenic, As. It's the chemical element. All right, P-type semiconductor doped with boron. Okay, and see here, you see we have our extra hole there. Okay. Diodes. So the best description of a diode that I can explain is a diode is a one-way check valve, or think of it as a door that only goes one way. You can go through it, but you can't go back the way you came. So you can go through the door, but you can't go back the way you came. Okay, a two-terminal semiconductor that acts as a one-way check valve to current flow. The schematic symbol of a diode shows the device's direction of current flow through the device. If a diode is inserted in a circuit so that it allows current flow, it is forward biased. If a diode is inserted in the circuit so that it does not allow current to flow, it is reversed biased. So you're going to see this in the following slides. The positive terminal of a diode is the anode, and the negative terminal of the diode is the cathode. And how I keep this straight in my mind is, if you think about conventional flow of electricity, we flow from the positive to the negative. So positive is first and negative is last. The anode is first, the cathode is last. And I think of that A to C. So A comes first in the alphabet, C comes last in the alphabet, as far as anode and cathode go. And so that's how I keep that straight. So I know that the anode comes first, just like positive, like our voltage flow is positive to negative, anode to cathode. And this becomes important when you're playing with light-emitting diodes and things like that. All right, so here's our diode schematic symbol. So here's our cathode, and again, it's our negative, and our anode, which is positive. And the stripe indicates the cathode end of the diode. Now, that's great, but we don't typically, we don't see these diodes often. They're not out in the open where we can read them. So what we're usually reading is this right here. We're reading a schematic. And so we're going to find out that the anode is this end here, and this would be the positive up here, and down here we would have the cathode. So that's basically what you're dealing with. You've got your anode and your cathode, and so this is positive up here. Select that pin again, positive up here and negative down here. And so the current flow will come from the positive, and then we'll have the negative here. Okay, so negative to ground. Okay, so that's our flow through our diode, and that's that's basically all you need to know about a diode, is that it is a one-way check valve. Once we come through here, we cannot go back. We can go through, but we cannot go back. And there are some special types of diodes that will allow some reverse biasing, and we'll talk about that. But on a conventional diode, we will not be able to go back. Okay, diodes will not permit current flow in the forward bias direction until 0.7 volts is dropped across the diode. A diode will always drop approximately 0.7 volts regardless of the current or voltage in the circuit. Diodes have a rated limit to reverse bias called a inverse voltage rating. If the inverse voltage rating is exceeded, the diode will be destroyed. Okay, so I said it can't go backwards. Well, it can't go backwards without damaging something. Typically, we don't use diodes as sacrificial lambs. We're not trying to destroy the actual diode itself. We are trying to make sure that we are stopping that voltage. So, but you can damage a diode in testing. So if you are using a power probe, which we're going to introduce you to, or you are jumping wires, you really do need to be careful of polarity of circuits that have a diode inside them. All right, so here we're diode testing, okay, with a DMM. And what you're going to find on your DMM is that there is a diode setting, okay? So you are going to use your common here, okay? And you're going to bring it to the anode side, and you're going to bring your positive red lead to the cathode side, and you're going to test it. And what you're going to find on a good diode is you're going to have over limit. Okay, that means that there is so much resistance your meter can't even read it. It's over limit or out of limit. Some people will also say that that stands for open loop, meaning the circuit is not connected. Okay, let's see. Now, if we forward bias test the relay, now we're taking our red lead and we're coming to the back here, and we are testing from through the anode to the cathode. Now we'll have 0.7 volts, and that is correct. That is showing that these two tests will show that this diode is working correctly. All right, so here's one of our favorite diodes. We're going to see these on a regular basis. This is the light-emitting diode. So if you've owned a modern flashlight in the last couple of years, it probably is using an LED. So LEDs are great. They produce lots of light and consume very little actual voltage or current, so which is nice. So here we have, again, a light-emitting diode. So we have to circle around it, which lets us know it's a little bit more of a component. It also looks about like a diode would. And then we have our two arrows. So that means that something is actually coming off of our diode, being emitted. We could have heat waves over here like that, but this is our light. Okay. All right, Zener diodes. In the forward bias direction, a Zener diode acts like a regular diode and allows current to flow. Okay, so totally normal, right? A Zener diode has a rating referred to as the Zener voltage. Once the Zener voltage is reached, the reverse bias direction of the Zener will switch on and conduct current in the reverse bias direction. So one of the places we're going to see a Zener diode is in our alternator. Okay, so we're going to see this happen in our alternator. So we'll get to experience this a little bit. All right, bipolar transistors. Bipolar transistors are made up of P-type and N-type junctions. There are two major types of bipolar transistors, PNP and NPN. A NPN, I'm sorry, I just said that right, I'm wrong. A PNP type is a sandwich of N-type material between two slices of P-type material. And inversely, a NPN type is a sandwich of P-type material between two slices of N-type material. Now, what this is going to do for us with an NPN is that we have a collector. Okay, here's our N. We have a base, and we have an emitter. Okay, and this is what that's going to look like in as far as a transistor goes. Okay, bipolar transistors. The P-type layer of NPN transistor is the base. One of the N-type layers is called the emitter, and the other N-type layer is called the collector. the emitter, collector, and base are labeled on the transistor itself as E, C, and B, emitter, collector, and base. So when you play with these components, you'll get to see that. We will do this in lab. We will get to experience this. Transistors amplify low-level signals to a higher-level signal. Okay? Transistors act like switches similar to a relay. Bipolar transistors continued. The collector of a bipolar transistor is connected to the positive terminal of the supply voltage. The base of the bipolar transistor is connected to the small signal that will be amplified. And the emitter of the bipolar transistor is connected to the load device, and the load is connected to the negative terminal of the supply voltage. All right, the negative terminal of the supply voltage. So in this case, we have our collector, our base, and our emitter. And here is what our base voltage is. Okay, 112 milliamps, 112 milliamps. And then look here, we're having 11 milliamps. And I'm sorry, I said that incorrectly. Let me back that up. So on the top side, we have 11.2 milliamps. Which would read like this, 0.0112 amps. Okay, and then down here, because of the 100K resistor, we're going to move our number yet, over a few more decimal places. And so now we have 0.000112 microamps. Okay, and that's what's being put in at the base. And what our output is 11.3 milliamps. Okay, so the transistor permits the collector current of 100 times the base current to flow through the emitter. Okay, and this is a typical circuit that we are going to see in our electronics. Now, the electronics are designed this way. However, the practical application of this is within the module, but we are not going to actually diagnose this problem a ton of the time. What we are going to look for is inputs and outputs, and when we don't see that output, but yet we see the correct input, oftentimes we're going to assume that the transistor inside the module is bad and replace the module itself. And we'll do that through guided diagnostics. This isn't something that you have to worry about trying to memorize. All right, NPN transistor used as a switch. So here we have our collector, our base, and our emitter. So when these two are less than 0.7 volts, the switch will be open. When these are equal to 0.7 volts or more, the base will basically will close rather, and the switch will be closed, and then we're using that as a switch. Now this is something you're going to see all the time in our vehicles with smart switches and switches that no longer really carry current. The switch is just a signal to the module of driver demand. Instead of actually closing the switch and having current flow over that switch, now we are, it's just an input to a module, and the module is actually outputting that. So you will see this quite often inside of our current model vehicles. All right, transistors connected as a pair, as a Darlington pair. A Darlington pair permits a small current to control a very large current. And you're going to find this again in relays. We talked a little bit about relays. So here we are using a small current to control a much larger current. And you will see this with a small transistor connected to a MOSFET, a metal oxide transistor, field effect transistor. I almost had a slip there. So as you're looking at this, this is just that relay. controlling, one small input controlling a larger output, basically. All right, field effect transistors. So FETs are controlled by voltage, not current. The drain of a FET corresponds to the collector of the bipolar transistor. The gate of a FET corresponds to the base of a bipolar transistor, and the source of a FET corresponds to the emitter of a bipolar transistor. We're going to get into this quite a little bit. Do your reading. Try to soak it in as much as possible. But this is something that will hopefully be a whole lot clearer at the end of the term than it is at the beginning. So take a minute, try to understand this. If you don't get frustrated. Don't feel like you're in the wrong place. This is something that's going to take you a little while. Again, basic electronics, yeah, there's nothing basic about it at this point in time in your career. It's very complex, and you're learning some new concepts, so don't be frustrated. The voltage difference between the gate and the source controls the resistance between the drain and the source, and so we'll talk a little bit about that going forward. But just so you understand, this is just like our relays. We are controlling an output with an input, and that's really kind of what you need to know about this at this point. So an N-channel JFET schematic symbol. So here you have your gate, you have your drain, and you have your source. Okay, and that's really, the gate is really what's being is really the input. The drain is the output, and the source is the voltage that we are trying to control. Okay. P, the P-channel JFET. Okay, and if you look at this, you have your drain, you have your source, and you have your gate again. And the voltage between the gate and the source equals 0. So the gate and the source, the voltage between the two, equals 0. So the switch is closed. The voltage between the gate and the source, so the gate and the source here, is equal to 4 volts. So the switch is open. The P-channel JFET is similar to a normally closed relay. Okay. So in a normally closed relay, it is closed all of the time at 0 volts. And when we add voltage, we're opening that switch. So different applications. All right, here's that MOSFET. So metal oxide semiconductor field effect transistor. So you have your gate here, you have your drain, and you have your source. And the N-channel E-MOSFET and the P-channel E-MOSFET, just different with the flow, how things are actually flowing. Okay, and we're going to talk about this quite a bit. So let this try to soak in. Do your reading again. If you don't get it, don't be too frustrated. It's very complex at first, and we'll start to get to it. Just remember that the real applicability of this is just in the fact that you know that these components live inside the module that you're testing. It is not. This training is not to make you think that you're going to have to open up a module and do these tests. That's above technician level. You probably are not going to see that often. All right. Drivers. Drivers are transistors used to switch high current devices. So we kind of talked about this before. That when the transistor is providing a path to ground, it is described as a low side driver. When a transistor is a device providing a path to ground, it is also said to be sinking. Okay, sinking, drawing it down. Okay, drawing it down to ground. When the transistor is providing a path for positive voltage, it is described as a high side device. And we'll talk a little bit about high side, low side. I think we did a little bit in one of our videos, and but again, that's from our schematic: high side, low side. So positive side, negative side. So we'll talk about that. So again, it's the high side driver, it's the low side driver. Sinking, not a term I use a lot, but I have heard it. It is synonymous with that low side driver. All right, a low side driver sinks current to the ground. So here we have, if you're following my cursor here, you're going from your battery or your positive voltage source over here. You're going through your solenoid winding, and your solenoid winding is being grounded by the low side driver. That low side driver, is connected to ground in the module itself. Okay. The high side driver sources current to the load. So in this case now, if we follow this, we have our high side, we have our driver. So our driver is now getting positive voltage from the battery, and the driver inside here, the transistor in here, is outputting the positive side, and we're going through our solenoid windings and finding ground at the chassis. All right, here's your tech tip. A device controlled by a low side driver located inside the electronic control module will typically be connected to a positive voltage at one terminal and the electronic control module at the other. And that's how we know. Remember, when we're looking at a schematic, we have to find that path from positive to negative. So if we are looking at this device and we find, okay, our fuse is at the top, we go down, we don't find, we find the component, and then lower down in the schematic we find the ECM or a module, then we know that that's a low side driver. If we do that same thing, if we find the positive voltage, then we have our ECM, and then away from that ECM, then we have our output that we're looking for. Well, then we know that that is a high side driver. The positive voltage is being supplied and not the negative. And we'll get more into that as well. All right, voltage dropped across the transistor collector to emitter. So what we're going to see in this case is 6.4 volts dropped across that. And with this 500 ohm resistor here, we're going to see this current draw of 0.0113 amps, or 11.3 milliamps, so 11.3 milliamps. And so we're sharing the voltage, right? We're practically dividing it, but not quite, but practically. So here we have 5.6 volts of output. And remember, all that voltage has to be used by the time it gets to the ground. So here's a transistor acting like an amplifier. So at the top here we have 23.5 milliamps, and here at the base, so at the collector we have 23.5 milliamps. It's here at the base we have 235 microamps. Okay, but our output here is 23.7 milliamps. So here we're actually amplifying. The transistor is saturated. Increasing the base current will not result in any additional collector emitter current. The transistor is acting as a switch in the on position. Okay. All right, as always, I'm going to let you read through this summary. You may need to pause it to read through. I'm just going to click through it pretty quick. You should read this. You should try to be understanding. You should try to understand, I should say. You should try to understand what all of these all of these terms are. Understand what's trying to be conveyed. If you don't get it, don't get frustrated. Like I said, we're going to continue to work on this. But one of the things you need to be expanding at this point in time is your vocabulary, your electrical vocabulary. And so you should be reading through this. If you don't understand one of the words, one of the terms, you don't understand what a rheostat is, you're not sure what a potentiometer is, you need to go back and read the chapter and try to solidify that.